Today we are exploring AI skills within Markdown files. We will cover the mechanics, operational efficiency, practical implementation, and the scaling strategy. First, what exactly does it mean to create an AI skill in a Markdown file? Instead of hard-coding complex prompts directly into your application logic or configuring them through a proprietary web interface, you encapsulate the entire behavior of an AI agent within a standard .md file. This text file acts as a standalone, portable blueprint. But what exactly do we use these specific files for? We use them to create a modular, reusable library of distinct quality assurance capabilities. For example, you might have one Markdown skill file dedicated entirely to analyzing UI automation stack traces, another for generating test data, and a third for translating acceptance criteria into automated test scripts. The body of the file then uses clear Markdown headings to separate the operating context, the step-by-step instructions, and the strict output schemas. Why is this approach necessary, and what problems does it solve? The primary advantage is absolute independence from any single large language model provider. You can take the exact same Markdown file and feed it as a system instruction to OpenAI's models, Anthropic's Claude, Google's Gemini, or even a local model running on Ollama. Furthermore, treating prompts as standard text files allows you to leverage existing version control systems as Git to track all behavior changes. Next, let's address execution mechanics, loading strategies, and token efficiency at scale. How many skills should your repository contain? The industry best practice is strict granularity. You should maintain dozens, if not hundreds, of highly specialized single responsibility skill files rather than a few massive multi-purpose ones. Now, if you scale to hundreds or thousands of skills and use them in an autonomous agent or an IDE like Cursor, automatic routing becomes a challenge. If the system has to evaluate 1,000 files simultaneously to decide which skill to use, a naive approach will flood the context window and cause massive token inflation. To prevent this, advanced architectures implement semantic routing. Instead of exposing all text files to the LLM at once, the skill metadata is indexed in a lightweight vector database. This operation is using less tokens than reading whole files. By decoupling skill discovery from prompt execution, your input token usage remains optimized. Let us ground this in a practical example. Imagine your continuous integration pipeline fails overnight due to a flaky UI test. The playwright execution logs show a timeout exception while waiting for a DOM element, but the raw output is massive and difficult to parse. In your repository, you have a specific file named analyze-element-timeout.md. Markdown body defines the operating context. It explicitly states, you are a senior automation engineer analyzing a playwright timeout exception. Identify if this is a genuine application bug or a test script synchronization issue. Finally, the file dictates the exact JSON structure required, a Boolean flag for application bug, a one-sentence root cause, and a recommended code fix. When the failure occurs, your framework retrieves this exact file, injects the failing stack trace into the template variables, and executes the API call. Instead of a human spending 20 minutes reading logs, your pipeline automatically attaches a structured, highly accurate diagnosis directly to the Jira ticket in seconds. Finally, how does this structure position you for the evolving ecosystem of AI marketplaces and plugins used by enterprise? Plugin is the package that bundles one or more skills for distribution, and the marketplace is the central catalog where developers discover and install those plugins. These files can be immediately exposed as custom tools within frameworks like LangChain or registered as enterprise plugins inside internal developer portals. Thank you for watching QA Ops. Subscribe for more technical breakdowns.